you might say, how did that happen if the forces point oppositely? Well, the forces point oppositely, but they also are on opposite sides of the pivot, so the torques are actually the same way. They both want to drive the system counterclockwise, so there is no doubt that the net torque on this will be positive or counterclockwise, and the angular acceleration, of course, is accordingly the same way. So while the center of mass might stay put, the rest of the system will certainly not. The rest of the rod will actually pick up and go faster and rotate. So we're going to put this thing into a rotational state. Let me try to demonstrate this in some fashion. This means some kind of object that's sort of like a rod. Anyone have a meter stick with them? That's an odd item to carry with you. I guess I'll have to show you with this eraser or something. Oh, maybe this stapler. I just need some kind of object like this. So if I come at this object exerting forces, one like this and one like this, what you can see is that if I maintain the orientation, what I do is I just rotate it in place, right? Do you see that? So it kind of looks like this, okay? So the center of mass stays put, while the rest of the object can be angularly accelerated around it, okay? So that's one case where the net force is 0, but the net torque is not. Let me go through all the permutations until I've convinced you that they are independent, okay? Let's do this. Let's apply both forces in the same direction and placed like this. So, okay, is there going to be a net force? Yes, for sure. Then both of these are in the same direction. Now, as far as describing the direction of that, well, it's not so there's no universal standard like plus and minus for rotation. So this is where we might set some axes. If you want to set your standard axes like this, then what would we say is the direction of the net force? Minus y direction, right? So the net force, and I guess I'll say the acceleration of the center of mass, will be in the minus y direction. So the center of mass is constrained to accelerate in that direction, like so. So the center of mass has to move along a straight line. And once again, if that has to move along a straight line, that becomes the de facto pivot, because if another point was the pivot, then the center of mass would have to go in some kind of circular fashion around it. So the only possibility for a pivot here is the center of mass. So let's take a look and see, and draw our circles once again around, with the center of mass, of course, being in the middle. So we look at that force. What's the direction of that torque? It's positive or counterclockwise. So if it were up to that force, this thing would angularly accelerate counterclockwise. But again, it's not just up to that force. We have to consider all of them. So this one would want to drive it around this way. What's the direction of that torque? That's negative or clockwise. It wants to drive it around the other way. And if these are equal forces at equal leverages, both tangential, then what happens? The net torque is actually 0. So the net torque and angular acceleration are actually nothing. So we don't get any rotational motion here. So I can show you this as well. Let me use this. This is a little more friction-free than this stapler. So that's what this looks like. I'm going to apply two forces in the same direction. and it just moves forward. It just has translational motion, but no rotation, right? Now, that's of course assuming that I push equally with both forces. What would happen if the forces that I pushed, they're both forward, but they're unequal? It would spin, right? Because one of the torques is going to win against the other one. So I could do that too. I could show you, I could push harder on one side than the other, and it indeed is going to rotate, angularly accelerate as it moves forward. In fact, the easiest way to perhaps do that is to just apply one force off center like this. If I exert one force, the center of mass is again constrained to move forward. But now that that force also has leverage against that center of mass, it'll also cause a torque. So this would be an example where neither is 0. You have both net force and net torque. So if you're starting to think that when one is 0, the other one's not, because of the first two cases I happen to do, that's not the case, right? I happen to have in this first one that the net force was 0, the second one the net torque was 0. They can both be non-zero, like this. I guess I could show you. So I go to the eraser. I'm going to give it just a single whack off center, and you can see that it both accelerates the center of mass forward and exerts a torque, right? So they could both be non-zero. They could both be 0 too. You could do that like this. If you did that, well, the net force is clearly 0. But that really only verifies for you that the center of mass doesn't budge. The net force is 0 here. But you can also see that they are exactly going to oppose torques, so the net torque is 0 as well. If you want to see that, that's easy. I'll just go up to the eraser and try to basically pinch the end, okay? Doesn't move, right? So I'm exerting two forces. Those forces cancel, and their torques cancel too. Okay, so those are all the different possibilities. So that's kind of talking through these things, being able to come at a situation, ask if the net force is 0 or not. There, you do not care whatsoever where the forces are applied. You just tally them up. And when you find that you have a net force that informs the center of mass only, doesn't inform any other point, if you want to know about the other points and whether there's not any rotation, you look at the net torque. Now when you're trying to look at torque, you need to consider, is there a force? Does it have leverage? Does it point in the right direction? And does it tend to drive it counterclockwise or clockwise? Okay, are there any questions on this before I move forward? Yeah.
Could you explain the concept of the acceleration in that case being...
Which case, this one?
In any of the cases, really. It doesn't seem like the center of mass is moving. It seems like it's spinning, but you're saying that the acceleration has a directional arrow?
In some of these cases, here it didn't. The first case, this one it did. And this one it did. This one it didn't, right? So which case are you...
I guess, is that assuming that the object is also going to move completely, or because it seems to me like it would just continue to rotate around itself?
That would be the case here, yeah. So if you applied equal and opposite forces on opposite ends, it would just rotate in place. And that's because there's no net force, so the center of mass can't move, right?
So in those other cases, then the entire object is also moving?
In this case, the only thing that's happening is that it's moving down. It's not rotating. The whole object, including the center of mass, is just going downward. Okay. In this one, the center of mass is going downward, and it's also rotating. So it goes like that.
Okay.
Okay, so this is kind of moving into the class of problems called static equilibrium. And again, these are problems that are challenging. And so what I'm going to do is I'm going to kind of sketch out most of the good bit of the strategy first, tell you kind of what are the basics, go through an example that's relatively straightforward, and then come back, do a more difficult example, and amend my problem-solving strategy to account for all the different twists and turns that there could be. So what is static equilibrium? It's something that's static, it's in equilibrium. It's kind of redundant. It's doing nothing, okay? So an object in static equilibrium is one in which the center of mass stays at rest, and there's also, it's not spinning. It stays not spinning. So it is the most boring object possible in some ways, right? It's doing absolutely nothing, but if you're building a bridge or a building, this is a very important feature of it, okay? So we need to figure out under what conditions can it stay doing nothing. Well, the fact that the center of mass stays at rest implies that the net force on the object is 0. I specifically draw that as an arrow because you cannot assume the reverse. If someone just tells you the net force is 0, it doesn't mean that the center of mass staying at rest. It could also be moving at constant velocity, okay? So don't run that arrow in reverse by mistake. If something stays not spinning, you can infer that the net torque is 0. And again, then the reverse is not necessarily true. Okay, it could also be spinning at a constant rate if all you know is that the net torque is 0. So, what we basically have are two equations that have to be satisfied in order for this thing to be doing what it's doing, which is not doing anything. So here are my steps. When I attack one of these problems, of course, the first thing I want to do, as always, is to identify my object of interest. So you can notice that's a common theme. That's usually step one for all of these problem-solving strategies. Pick something out of the universe and focus. Now here's what makes these problems a little bit tricky right from the outset. It's usually not just a single object. Usually it's a group of objects that might rotate together. So I like to call it a rotational system. So it's really objects of interest. I'll call a rotational system. So you want to pick a good grouping of objects. Now what goes into the rotational system, what goes into them is things that if they were going to rotate, they'd rotate together. So they're kind of all grouped together. So it's like a cohort of objects, right? So these are things that would rotate together if they were going to rotate. Although in this case, we are going to make sure that they don't actually. Okay? So that's your first thing that you set yourself up for success, is picking the right group of objects. Okay? Then you identify the external forces on that system. And it's really important that you only identify things that are coming in from the outside world on this system. Much like we did in momentum conservation, the internal forces are something that we don't care about. So for instance, if you have, as we'll do in the very next example, we have a seesaw, okay, with two people on it. Our rotational system is going to be the seesaw, plank, and the two people. That's the stuff that would tilt together. So you want to only include things coming in from outside. You don't care about infighting, okay? So make sure that you don't accidentally include anything that's internal. Because something that comes from inside is never going to cause it to the system to rotate as a whole. That's the rotational equivalent of picking yourself up and carrying yourself out of the room. Something from inside could never cause the whole thing to move in a given direction, okay? So, once you have that, this is what makes this challenging. You run through your entire force problem solving strategy, and that of course involves breaking up your forces into components and all that business. And what you end up with, of course, is F net x equals max and F net y equals may, but luckily, no acceleration here. So of course, that alone was plenty of fun stuff that you saw in homeworks 4 and 5 and 6. That's just one little piece of these problems, okay? So there's a lot going on. But you haven't yet even considered your other piece of information, which is that your net torques also have to be 0. So all of the torques caused by all those forces also have to cancel. So you also have to compute the torque due to each individual force, and then add them up and make sure that's 0. So what do you have? You have not 1, not 2, but 3 equations that have to be satisfied in order for this thing to stay in static equilibrium. So there's a lot that has to go right before the system will stay put. Well, that means that if I wanted to, I could leave out up to 3 unknowns, and you could solve for them, right? Because you can solve 3 equations, 3 unknowns. These systems are so well prescribed, I can leave out up to 3 different things, and you can find what all of them are from the context of the others. Now, I'm generally not going to do that. 3 equations and 3 unknowns. We've got to save some fun for physics too. Okay. So usually, it'll be one of these two, one force equation, and the torque equation, and you'll have a 2 equations, 2 unknowns system. Now you might ask, well, isn't that just kind of swapping out, instead of having 2 force equations, x and y, and solving for 2 unknowns? That's what you did in homeworks 4, 5, whatever. How is this really any better to now throw away 1 force equation and introduce the torque equation instead? Well, let me remind you that the torque involves all sorts of things we never saw before, right? Torque has r in it, for instance. It's a distance. So we can ask for distances of things, like where should forces be applied? That's something we never would have been able to address before, because for the force method, it doesn't matter where those forces are applied. Okay? So it opens up to a whole bunch of unknowns that get involved here. Like where to apply forces and at what angle to apply forces and all this stuff that wasn't involved before. That's the basic gist of a static equilibrium problem. And there's even more to it. Let me remind you that in order to compute a torque, that torque is computed around some kind of pivot. And we're going to learn in some problems that what the pivot is not very clear at all. So there are strategies for identifying and picking pivots as well for doing your torque computations. So I don't even want to get into that yet, because this is all plenty. So the first example I'm going to do, as I mentioned, is a seesaw. So a seesaw has this pivot that everyone just says, okay, seesaw has a pivot. Don't have to think much about it. Okay. So let's try one out. So my first example, I'll have a seesaw. Let me put some masses on here. You can imagine these as people, but they're going to be way too small to be actual people. This will be mass 1. I guess I'll label it 1. And mass 1 will be 2 kilograms. Let me make sure I get the numbers the same as my notes here. So that'll be 2 kilogram mass, and that'll be 3 meters away from the pivot. And then my question is, my mass 2, which will go on the other side, where do I put it to balance? So again, this is a pretty straightforward problem. If you've ever been on a seesaw with a little kid, you know you have to sit closer to the middle than they are. Yes? Okay. So it's going to be somewhere closer here. I don't have to spoil the surprise by putting it somewhere over there. It's not at the end. And I want to know what's this distance. Actually, I don't know why I labeled them 1 and 2, because that's going to accidentally make me think that they're 1 and 2 kilograms. I should have labeled them mass 1 and mass 2. That's better. I like that better. In fact, you might even just be able to look at this and go, oh, that's easy. It's twice the mass, so it's half the distance, right? The answer is 1.5 meters, right? That's totally correct. All right. So when I show you a couple different ways to get it, won't be too big of a surprise. It'll gel with your everyday intuition. Let's take a look. I'll give you 2 proposed methods for getting this, one of which is the new stuff we're talking about now, torque, and the other one, which will be old news. You can use the center of mass method for this. And the reason why you can use the center of mass method for this is because the whole system, the 2 people and everything, the plank, is being held up by a single support force, right? The seesaw hinge or seesaw triangle, whatever that, I don't know what that part of the seesaw is called, this thing. Okay, this thing is the only thing holding up the whole thing. And we learned that if you have a single support force that's holding up a system, the balance method tells us that that has to be at the center of mass. So apparently, the center of mass of the system is right here. Okay? So since we have a single support force, and I do emphasize single support force, it must be at the center of mass. So this right here, you're doing this homework problem right now. There, if you haven't already, it's the grocery basket problem, right? So it says something about where do you put the milk so that the center of mass ends up at the middle of the basket, right? Why do you want the center of mass in the middle of the basket? Because it's where the handle is, right? So you don't want it to tip over. Okay? So try it that way, and you will get that it will be 1.5 meters. I'll leave that to you. You're already doing it on homework, so you don't have to do it again. So I want to focus on the new method, the torque method. And this is static equilibrium because we're asking, where do we have to put that other mass so that it balances? So it is in static equilibrium. So let's go through our steps. Our rotational system is all the stuff that would rotate together, and that will be the 2 masses and the plank. I guess I should have written down that the plank is approximately massless. So, but it is a handy thing to think about, including in your system, okay? Because those are all the things that if there was some kind of imbalance, they would all go together, right? The 2 people in the plank would all rotate in conjunction. Okay, so there's my rotational system. Now I'm going to identify external forces that act on it. Well, the force of gravity, that's external, that comes from the Earth. The Earth is not a member of my system. I could certainly take the entire weight of it and have it pull down at the center of mass. But that would not be helpful because it's already condensing the two masses into one, and I want, so I'm going to propose to just keep these two separate. I can think of the force of gravity as pulling on both parts of that system. Those are two external forces of gravity. So even though I'm imagining the system as one, it's still handy to think of the two pulls of gravity separately. Okay? But that can't be it. There's one more external force, because if it were only those two, this whole system would be in free fall. What else is there? Normal force. Where does that act?
At the center of mass.
It acts where the actual physical contact is with the support. So that's another thing that I should probably have written down here. It's not